Okay, can we move on?
Yes, sir.
Okay, so I hope when you go back home or tomorrow morning for you, you can play a bit with the program, but also with the other. They are very simple and they can be useful to you to understand better the concept that we have discussed yesterday and today. Okay. Okay, now we will talk about two quite important techniques in array processing that are called shading and null steering. Let's try to understand. Okay, we introduced the classical beamformer. So far, the only beamformer that I talk about is the classical beamformer. It's a special filter, an FIR special filter with impulse response matched to the array response. So it's a matched filter in practice. And then we have seen that the classical beamformer can be used to estimate the directional arrival of a number of targets. In general, the estimate is biased, but under some condition that we have described in detail, the estimates can be good, can be unbiased. So we can estimate the distribution of the power in the environment as a function of the directional arrival. So we can estimate the angular or spatial power spectral density. And the estimator that we obtain by using classical beamformer is basically the equivalent of the Bartlett method. So it's basically the average periodogram. Now, the other thing that we have understood is that if we use a Euler array or a linear array, the resolution, so the minimum distance between two different sources, two different targets, that allows the beamformer to separate them in angle. So the resolution is inversely proportional to the array aperture. And we have discussed how to maintain good resolution by using less sensor, resorting to sparse architecture. In general, the resolution, roughly speaking, is on the order of the array beamwidth. And so it depends on the number of sensors. But the resolution is not the only issue. So if you look at, for example, the beam pattern of a classical EULA, the resolution is somehow depends on the beam width, so the width of the main lobe. But another problem is created by the side lobes, and we have understood that the side lobes of strong sources, you don't see them, you don't realize that in your data there are, let's say, 3 sources, but you can see only 2 because the third one is weak and is covered by the side lobes of the strong sources. This phenomenon is called masking. So resolution is one issue, but another very important issue is masking, because obviously the power of different sources may be different. Maybe, the signal reflected by different targets can be different because one target is farther than the other. So when you receive a reflection, this reflection is much weaker than the other. So masking does not allow you to understand well, how many sources, how many targets are in the environment. So it's a problem. How can we reduce the masking? To reduce the masking, obviously, we should reduce the age of the side lobes. No, I mean, we don't have alternatives. So we should find a technique that allows to reduce the age of the side lobes. And the shading technique is exactly a technique which is non-adaptive. It's a non-adaptive technique that allows to reduce the side lobe. So the idea is the following. So far, we didn't introduce any weighting in the data. So it's like we observe, we sample in space, and so it's like we have a rectangular window on the space, and we sample only within that rectangular window. So high side lobes are due to the fact that a rectangular window has a very abrupt change. And I mean, if you are familiar with Fourier analysis, if you have a rectangular signal in the time domain with an abrupt change, in the frequency domain, you have a spectrum with high side lobes. If you want to reduce side lobes, you should make the transition less abrupt. So you have to introduce a smoothing transition in the time domain. Well, basically the idea is to apply exactly the same technique in space and angle instead of time and frequency. So the idea is the following. Introduce a weighting on our beamformer. So we multiply each element of the impulse response of the spatial filter by a window, W, and in order to reduce the side lobe, this window should have a transition from the maximum value to the minimum smoother than a rectangular window. So this operation is called, usually when you work in the temporal domain, this kind of operating is called windowing. When you work in space, typically we use a different term. And we use the term shading or tapering, but the meaning is exactly the same. So windowing, shading, tapering are synonymous. And so, for example, if you have a EULA, the ideal array response is this one. If we introduce a tapering, so we build a filter that is no more matched to the array response. So we basically implement a mismatched filter, but the mismatching is introduced for a specific purpose to reduce the side lobes. So the problem is how we choose these weights, W1, W2, Wm. So you can represent the tapering operation in this way. So we introduce a phase shift in the signal collected by the M sensors. But in addition to the phase shift, are these terms here. When you multiply by e to j something, you are basically introducing a phase shift. Okay, with the tapering, in addition to the phase shift, you introduce a weight. And then you sum, and you get the output of the beamformer. Now the problem is how to design this weight in order to reduce the side lobes. Now, there is no optimal solution. So there is no golden rule that tells you what you have to do. You have to understand what is the trade-off here. And once you understand the trade-off, you can be able to find a good window for your application. But please understand that it does not exist the optimal solution. It's up to you, based on your experience, to find the window that provide the best trade-off between different needs. So I will try to explain why there is a trade-off. So if you do L window in MATLAB, you find many windows: Bartlett, modified Bartlett, Henning, Blackman, Bowman, Chebyshev, Gaussian, Emmy, N, Kaus, and so on. There are so many windows that it's clear that no one is optimal, but they just provide a different trade-off between masking and resolution. The trade-off, as you will understand, is between masking and resolution. Remember one thing: if we multiply, in this case, in the space domain, in the transform domain, which is the angle, the effect is a convolution. And so the beam pattern that you obtain is the convolution between the ideal beam pattern that we obtain without window V convolved with the transform of the window. So, for example, if instead of a rectangular window, we use a triangular window, which has a smoother transition from the maximum to the minimum, what you get is a lowering of the side lobes. So in blue, you find the transform in the angle domain of the window. And without shading, you have the transform of the rectangular window, which has better resolution, but worse side lobe. Now, I mean, when you change this transition, what remains constant, it can be proved, is the area behind the beam pattern. So the area is constant. Now, maybe this is not obvious from this picture because it is in dB. But believe me, the area is constant because the area is the value of the window at zero leg in the middle. The windows are always with the maximum in the middle, and they are always symmetric. Okay, always positive also. So the area is constant. So the problem is that if you lower the side lobes, so if you push down the side lobe, one unwanted effect is always that the main lobe gets large in order to maintain constant the area. So no way you can reduce the masking effect only at the cost of a worsening of the resolution. So there is no optimal choice. It depends in your application if it is more important to reduce the masking or to achieve the best possible resolution. If you want to achieve the best possible resolution, you should not use the shaping. You should not use any window. So you introduce a shaping only with the purpose to reduce the side lobe. But this can be done only at the cost of a worsening of the resolution. So different window guarantee a different trade-off between masking and resolution. Okay, so this is the triangular window. Another very well-known window is the Blackman-Harris window. It is done like this. So you have a much lower side lobes. I decided to stop at -60, so the side lobe are below -60. And you can see you reduce a lot the side lobe, but at the cost of a large worsening of the resolution. Different window, different trade-off. This is the Gaussian window. So this is a Gaussian shape. Again, lower side lobe, larger main lobe. So no way to escape from this. The Gaussian window has a control parameter alpha. So different alpha, you get a different trade-off. Hamming window, another very famous window. So larger side lobe, smaller side lobe, worsen resolution. So Hamming is another. Kaiser is a very famous one. The Kaiser window has an extra parameter beta that controls the trade-off. Chebyshev has a unique characteristic that all the side lobe have the same level. So it's a uniform side lobe characteristic. So only the Chebyshev window has this property. And there is a control parameter, so you can control the level of the side lobe, and this is -20. If you want to push farther down, you can do. For example, you push down by 40 dB, but I repeat, obviously, you can achieve this only at the cost of a widening of the main lobe, so worsening the resolution. So, I mean, to find the right window, you need to have a bit of experience. So this is something that you learn with experience, and the best trade-off is different from one application to the other. This is the Chebyshev window with the -100 dB. You see that you can push down a lot the side lobe, but at the cost of worsening a lot the resolution. So this method is non-adaptive because you choose your window, you build your system with that window, and this is what you get. The idea is that if you push down the side lobe, whatever is the directional arrival of the other source of the jammer, if you reduce the side lobe, you reduce the risk of masking. This is the idea behind this method. So the shading or tapering technique is absolutely a non-adaptive method, and it works well if you have interference and sources distributed around the array, so coming from various angles. Now, sometimes there are cases where you know the directional arrival of the interference because you built your system and you know that from that angle there is a transmitter that creates interference. So in the case where you know the directional arrival of the interference, and instead of pushing down the side lobe by using the shading technique, it's better to put nulls in this particular direction. But this is possible only in those cases where you know a priori the direction of arrival of the interference. So the idea is the following. And so this technique is called null steering. So let's assume that you want to steer the beam in direction theta. And you know that from angle theta j, there is an interference. So we reconsider the previous design, fitted design problem. So if you remember, the approach was to assume that Ry is the density matrix. So we want to minimize the power of the signal coming from a direction different from the steering direction theta, subject to the constraint that the gain from direction theta is 1. So you want the signal that comes from angle theta to pass undistorted. So this is the non-distortion constraint. And this is the problem that we solved before. And the solution of this problem, as you remember, was the classical beamformer. Okay, if you want to put a null, the idea is to add the constraint in the optimization problem. And the constraint should be of this kind. So we want to kill a signal coming from direction theta j. So here we want the signal to pass. Here we want the signal to be cancelled. So we want to put a null in the beam pattern at the known angle theta j. So we solve this problem. And we solve this problem by using the Lagrange method. So we have two constraints, two complex constraints. So we have two Lagrange multipliers, lambda 1, lambda 2. To simplify the notation, I call A of theta, so the array response from the steering direction, and AJ, the array response from the direction of the interference. And we solve the problem. So we calculate the gradient. We calculate the gradient. I mean, this is quite simple, but I reported all the steps in the view graph. But if you need, you can find the gradient of a quadratic form on Wikipedia. So you calculate the gradient of this quadratic form. This is the solution. You express the solution this way. You set the gradient equal to 0 and you find the solution. So this is the solution as a function of the two Lagrange multipliers. How do we find the two Lagrange multipliers? By imposing that the two constraints are satisfied. So these are the two constraints. So we replace H with this here, and we impose that the two constraints are satisfied. So we have two linear equations in two unknowns, lambda 1 and lambda 2. So it's a very simple linear system with two unknowns and two equations. So you can write the linear system equation in matrix notation. So obviously this term here is equal to M, the energy of A. This is the energy of AJ, M. And this is the inner product between the two different vectors. So you can find the solution with the well-known rule of adjunct. So it is 1 divided by the determinant multiplied by the matrix of the adjunct. I mean, you can solve this linear system as you want. It's very, very simple. So finally, this is the solution. So these are the two Lagrange multipliers. This is the solution. And so you get the impulse response of the beamformer with null steering. So this is lambda 1 A plus lambda 2 AJ. And you can verify that the two constraints are satisfied. You replace this here and you find that the solution is correct. There are a couple of things that I want to comment about this solution. The first one is the following. The output of this beamformer is the following. So you multiply H Hermitian by Y, so you get this. Now, if you put this term in evidence, you can express the output as this term, which is just a scaling factor. And then in square brackets, you have two terms. The first one is the classical beamformer output. So this is the matched filter Hermitian that multiplies y. So this is exactly the classical beamformer out. So the null steering beamformer can be interpreted in this way. It is, I mean, you calculate the classical beamformer output, then you steer the beam in the direction of the interference, you measure the interference, then you know that the interference enter in the classical beamformer output through the side lobes. So you scale the interference and you subtract. So basically, this is like if you create two beams, one steered in direction theta, the other steered in direction of the interference. The beam steered in the direction of interference has the purpose to measure the interference. And then you subtract. So you cancel the interference from here. So this subtraction basically implements the interference cancellation. This is even more obvious if you calculate the beam pattern. So you calculate the beam pattern, it is the modulo square of this quantity. So you can express analytically the power beam pattern. Let me show the picture. So for example, if the interference is coming from 18 degrees, with the null steering technique, you can see you put a null at 18 degrees. So when you steer the beam in direction 0 degrees, the interference is cancelled, so it does not affect the measure of the signal that comes from 0 degrees. Instead, if you use the classical Euler beamformer, the interference is weighted by the side lobe, and if the power of the interference is large, basically it affects the measure through the side lobe. So with the null steering technique, you are able to cancel or reduce the effect of the interference, but remember, this is possible only if you know a priori the direction of arrival of the interference. Otherwise, the only thing that you can do is to lower the side lobes uniformly, and to do this, you have to use the previous technique, the shading technique. So they are two different techniques that basically can be used in two different scenarios. The null steering technique can be used only in the case where you know a priori the direction arrival of the interference. This is another example where you steer the beam at 30 degrees and the jammer is still coming from 18 degrees. So you have a hole here. The last comment, obviously, if you know that at this angle you have the interference, you never steer the beam towards the angle theta j. So the steering direction theta should be always different from theta j. Now, what happens? If the signal of interest is coming from a direction theta t, which is equal to the steering direction, so if theta t is equal to theta, the beam pattern is equal to 1. So this is the beam pattern. If theta t is equal to theta, so if the signal is coming from the steering direction, as correctly we want, the gain is 1. So it passes undistorted. If the signal comes from the direction of the interference, obviously it is killed. So if theta t is equal to theta j, so in place of theta t, here you put theta, here you put theta j. In that case, obviously the signal is killed because by construction, this beamformer kills everything is coming from direction theta j. This is exactly what we want to achieve. So I think we can stop here. And tomorrow I will show you how we can extend the nulling technique, the null steering technique, to the case we have multiple interferences. So far we have seen the case where we have only one interference, but this can be very easily extended to the case where there are multiple interferences. But what is important is that we know a priori the direction arrival of these interferences. If we don't know them, better to use the shading technique. Okay. I think we should stop here.
Okay, thank you, sir.
Any question?
Any question from anyone? If you have any question, please ask.
I cannot hear you well. So if you have a question, can you write in chat?
Yeah. If you have any question, please write on the chat box. So that will be easier for everyone.
I'm sorry, but the quality of the audio is bad. I cannot hear. I cannot understand. Okay, I mean, if you have questions, send me an email and I will try to answer everything, okay?
Okay.
Okay, thank you, sir.
There is no question. Thank you. Thank you.
Okay, see you tomorrow.
Okay, sir.